compounds, you guys have learned that it's based around what type of compound we have, right? We have ionic compounds, and that has some wrinkles in the nomenclature in terms of Roman numerals for things that can have more than one charge. And hydrates, as everybody learned in lab this morning or yesterday. And we just name those hydrates with the same prefixes, the Greek-based prefixes. So if there's 4 waters as part of the chemical formula, we would name it as tetrahydrate. We'd still name the ionic compound the same. We would just tack on whatever hydrate at the end based on how many we have. Right, so for instance, copper 2 sulfate pentahydrate. Penta means 5. Hydrate means that we're adding waters to the molecular weight, but they're not affecting the charges of anything because water's neutral. So the formula for that would be, so copper is a +2 because it's copper 2 ion. Sulfate, whether you have it memorized or not yet, SO4 with a -2 charge. So we need one of each of them to make it neutral, right? So the formula for copper sulfate has nothing to do with the hydrate. We ignore the hydrate part for now. So we can say, okay, there's our formula for copper sulfate. The pentahydrate, we just use a bullet operator, like when you have a bulleted list or a dot product, if you've taken linear algebra. And then we say, what did I say, 5 pentahydrate? And we just say, and we've got 5 waters. Right? This dot product is really indicating that this is not part of the ion complex. It's not really interacting that much with the ions. It's just the crystal structure needs these waters to be stable. If it doesn't have these, then it's not stable and it'll sort of break apart. Right? So ionic compounds are not too bad. You recognize them by looking for, if we have things where you have a positive ion, you can recognize and say, okay, that's a positive ion, that's a negative ion, therefore this is an ionic compound. Covalent compounds were anything that was neutral, that's all nonmetals, right? Where you can't look at the formula and say, oh, clearly that's a positive charge, that's a negative charge. So something like dinitrogen monoxide. Right, so this all should be reviewed. This was on the midterm. This was the easy version, right? Was when we just had all covalent stuff and we could just use the prefixes to say how many we had, right? Our one extra type of nomenclature we're going to add right now. So then covalent, which was all just use the prefixes. The last case is, what do we do? We have a class of molecules called acids. And an acid is basically a covalent, it's basically an ionic compound where your positive charges are hydrogens. So where your cation is all hydrogens, so you have enough hydrogen H pluses to balance out the charge completely, so you have a neutral compound. Right, so it'll look a lot like the formula for an ionic compound, except we won't have a metal ion. Right, so for instance, if we have, this was the one that got asked about the other day in class, is, well, if sulfate is SO4 2- and hydrogen sulfate adds 1 hydrogen, 1 H plus, and that makes it HSO4 -1. If we add another H plus, that makes it neutral. And that turns it into a compound we're going to call an acid. Right, so all an acid is still an ionic compound, but because we have hydrogen acting as the cation, it behaves differently than regular ionic compounds, and so we name it differently. Right, so the names for the acids are always based on what is the name of the anion. Right, and so we're always going, the anions, whether it's a polyatomic ion, or just something on the periodic table, they only have 3 possible endings. If it's something on the periodic table and you give it a negative charge, what does it end in? Ide, right? Chlorine with a negative charge becomes chloride. So if it ends in ide, when we name it as an acid, we're just going to change the ending here and add the word acid at the end. Naming it as an acid says that the positive charge is an H+. Right, so if it ends in ide, we turn it into, we put hydro in front, and then we use the same root, and then we put ic at the end. And we'll do examples of these too. But so anytime you can look at something and say, I recognize that anion, and it ends in ide, you're going to name it by saying hydro whatever ic. So if it's HCl, that looks a lot like sodium chloride, right? Except with an H+ as our cation. So ide, it ends in ide, so we drop the ide, and we would, so instead of chloride, it's hydrochloric acid. Right, so it's, I don't know why they don't just name it as hydrogen chloride, why we don't just name it as an ionic compound, other than the fact that acids behave differently in water than a lot of ionic compounds, and they're a lot more important physiologically than a lot of ionic compounds. So for that reason, probably historically, it probably has to do with the fact that they didn't realize that they were very similar compounds originally. We have to learn a new naming system.
So that's what that one is?
So
it should be hydrochloric acid?
Hold that thought. We're going to come back to that. Let's finish these up first. So that's, if it ends in ide, it goes to hydroic. What's another ending that we can have based on polyatomic ions? Ite and ate. If you look at your list of polyatomic ions, everything ended in either ide, ate, or ic. Or sorry, ite. Getting ahead of myself. If it ends in ate, we don't use the hydro prefix, and then we just still throw ic at the end and in the word acid. So nitrate becomes nitric acid. Carbonate becomes carbonic acid. Acetate becomes acetic acid. Right, so anything that ends in ate, this is how we're going to name it. There are 2 irregulars that are where you actually put an extra syllable back in. If it's sulfate, it's not sulfic acid. We actually put the UR back in for sulfur, so it becomes sulfuric acid. I don't know why sulfur gets special treatment, but it does. And same for phosphate. Phosphate becomes phosphoric acid instead of phosphic acid. But those are common enough words that you probably have heard those terms before, even if you didn't know what the formula was. So sulfic acid should sound wrong to you. Sulfuric acid probably sounds familiar at some level. If it doesn't, then we'll get it familiar and you'll just keep practicing with it. It's like learning irregulars in another language, right? Sometimes you just got to learn the weird things and deal with it. If it ends in ite, then it turns into OUS. So nitrite becomes nitrous acid. Nitrate becomes nitric acid. So chlorine is a good example because chlorine has all of these endings, right? There's chloride, chlorate, and chlorite. If it's chloride, that's HCl. So chloride becomes hydrochloric acid. Chlorate becomes chloric acid. And chlorite becomes chlorous acid. Right, so the formula is for chloric acid. Chlorate is ClO3 with a -1 charge, right? So to add enough H pluses to make it neutral, we only need one of them, right? +1, -1. So HClO3 would be chloric acid. What would chlorite be? What's the formula for chlorite? Yeah, the ites are just the 8s missing an oxygen, right? So if it was HClO2, ClO2 with the negative charge is chlorite. So that tells us we're going to name this acid as chlorous acid. All right, so this takes getting used to, which is why you have a 14-page ICA of practice ionic compounds, practice ionic compounds with Roman numerals, practice ionic compounds with polyatomic ions, practice naming acids, practice naming covalent compounds, practice naming hydrates. Just pages of this. And it doesn't usually make you, as a group, very happy with me, but you will do better on the nomenclature portion of the final if you do this. And the key is available, although there may be a couple typos here and there.
Sean, before you erase stuff, because on our polyatomic list we have like hypochlorite and hydrogen carbonates and stuff, does that matter? Can you still say like?
So hypochlorite would be ClO with a -1 charge, right? So if we made that an acid, we would need to add 1 H to it. It still ends in an ite though, even though it's hypo-ite, it still ends in ite, right? So we still would name it with this base. So it's hypochlorous acid, which is what's in, some cleaning product. Drano maybe? No, not Drano. There's a common cleaning product. Sodium hypochlorite is bleach, hypochlorous acid, something similar. I'm just totally blanking right now. It's something that if you've ever bought cleaning supplies, you've probably bought it before.
And then how are we supposed to differentiate if something has is an acid or if it's like a hydrogen carbonate? So it already has the H in front of it.
So hydrogen carbonate looks like that, right? It still has a charge.
Okay.
So this, if we have this with, say, sodium, one sodium ion would match the -1 charge of the hydrogen carbonate. This is still just a regular ionic compound because you have a cation and an anion that you can recognize. So we just say the name of both of them, sodium hydrogen carbonate.
So if you turn that into an acid, is it still
If you-
hydrogen carbonic acid?
If you turn this into an acid, we need to add one more hydrogen to make the charges balance out. So we don't say the hydrogen anymore because this is just carbonic acid. Carbonate, 8 is our second category here. So we just drop the 8 at the end and add it, acid, right? So carbonic acid versus hydrogen carbonate. Right, the second you add the extra H plus to make it neutral, changes whether it's an ionic compound or an acid, which is a little arbitrary, but we'll get used to it. One more thing I was going to say, if you weren't in class yesterday, this takes getting used to, like I said, but there are a few ways of memorizing this, and they're all really cheesy mnemonic devices. The one that I've heard works the best is my ride has hydraulics. I ate something icky, and Sprite is delicious. It's dumb, but hopefully you will remember that, or at least with a little bit of practice you will. And then, so I didn't know that when I first learned these, but I had a friend in high school whose name was Titus. So when I first learned this, oh, it and us, that goes together. That, of course, itis. And so now every time I teach this, I get to remember my friend Titus from high school, and now you too will remember my friend Titus from high school. It goes with us because it sounds like Titus. And things that end in I are usually the simplest ions, because it's mostly the things that are on the periodic table, right? So the simplest acids have the most complicated name. Is the other way I remember it.
How do you say the one for iodine? I couldn't figure that.
So iodide,
Right.
the formula,
Right.
iodide would be
H.
HI.
Yeah, right.
So the name for that would be hydroiodic acid.
It just looked funny. So
It does look funny. There's a whole bunch of vowels and not enough consonants in there, right? It also, I don't know if you have figured this out yet, you can actually ask Google what the formula is for chemical compounds, and Google will give you the formula. It also means you can make up some fun chemistry jokes. And you can say, here, we'll type it in. We'll do this together. This will be fun. What is the formula for, or even better, hang on. Do you know the formula for sodium hypobromite? And, oh, it didn't work this time. Normally, can anybody figure out what the formula would be for sodium hypobromite?
NaBrO.
NaBrO? Nah, bro. You know the formula? Nah, bro. Or you can say, Google, tell me the formula for nitrogen monoxide. And Google just says, no. It's dumb. But these are the sort of things that we went through in as chemists sometimes. This one in particular, I like nah, bro. All right, so the other question that was asked, started this whole thing, was what happens if these aren't dissolved in, acids have to be dissolved in water to be an acid. When they're not dissolved in water, we basically just name them like they're ionic compounds. We say the name of the cation and we say the name of the anion. So if you have HCl aqueous, that's hydrochloric acid. But if you have HCl as a gas, that's hydrogen chloride. Basically because it can't be an acid until it's dissolved in water. And this subscript here, aqueous, means dissolved in water. Right, so if it's not dissolved in water, you just name it as though it's an ionic compound. Say the name of the hydrogen, say chloride. Right, and this is the only one that it really shows up with. Almost all acids are so soluble in water that they're like those hydrates we were looking at. They will pull moisture out of the air to make themselves dissolved in water. Right, so H2SO4, sulfuric acid, about as concentrated as you can get it is, I want to say it's like 90% pure H2SO4. The other 10% basically is water you can't get rid of. And it doesn't really turn into a gas easily. Mark?
So when it's gas, it's just hydrogen chloride?
When it's a gas, it's just hydrogen chloride. If this was a gas, if we had some other system that was not like our Earth-like systems, or sorry, if we turn that to a gas, we would say hydrogen sulfate.
So that's hydrogen sulfate?
So this, when it was an acid, we would be in the second column, right? Sulfate, so it would just be sulfuric acid.
Okay.
Right, again, takes some getting used to. And it's a little arbitrary, but this is one of those things that's been around forever and likely will always be around forever as long as there are chemists. It's something that it's almost a rite of passage at this point where you have to learn acid nomenclature even though it's a pain in the ass. It's just the way it is. So I apologize, but I'm going to make you do it. All right, so the assignment then is available, and it has a pretty long background that has all the different types of nomenclature and when to use all of them. And it has, all you need to turn in is the report sheet, and I can give you a printout of the report sheet if you need a printed copy, or you can just do it on binder paper. I think that's everything that you need for that. Everybody from yesterday who's been working on it, am I forgetting anything?
Just the last page, but that's the percentage.
Oh, okay, yeah, that's some practice with word problems. We're gonna do some practice with that today anyway, so. All right. So now that we're 25 minutes into lecture, we can start lecture. That's not fair. That was lecture. It's just normally I would do that in lab. But we don't have lab on Thursday. All right. We'll save these quiz questions for next week, probably. We'll spend more time talking about crystal structures as we get further along here. Saturated versus unsaturated fats, though, is always interesting. Especially why are some fats better than other fats? Anytime we put a value statement, we use a value term on something in science, we have to identify better at what. If we're just talking about putting as much energy in as small a space as possible, then actually saturated fats are really, really good at that. They're just really, really bad if you want to do things like keep your cell membranes liquid, because they pack together really, really well. Saturated fats basically means that you have a big long chain of carbons attached to an acid group that looks like this. And these can be like 20 carbons long, 16 to 20 carbons long. And when they're all saturated, the VSEPR geometries are such that they pack really, really tightly together, like toothpicks in a box. However, if it's an unsaturated fat, that means that you actually have a carbon-carbon double bond in there somewhere. And what that does is it basically makes it make a right turn. So now picture your box of toothpicks and you take out 30% of them, kind of break them in half, but not pull them apart. So break toothpicks so it's bent, and now try to fit them all back into the same box. Doesn't work, right? Basically, by having unsaturated fats, you're forcing them to stay liquid at body temperature. But saturated fats can be solid at room temperature. We don't typically like solids in our bodies all that much, especially not in cell membranes. They're supposed to be fluid and movable. Right, so in terms of nutrition, unsaturated fats are better, and they also get used in what are called precursors, where you can take this compound and turn it into other things. It's like vitamin A. A lot of the proteins in your eyes and in your retina start off as unsaturated fatty acids. Then you have them react a few more times, and you can make vitamin A and various other proteins and molecules that are really important. That's actually one of the things that taurine does for cats. Taurine is a molecule that gets added to energy drinks for some reason. It's totally unnecessary for human life, but cats actually need it added to their diet. It's a vitamin for cats that has this unsaturated point in it, and it basically allows the cat's eyes to function properly. So if you ever have cats and you buy them dog food, if you do that for too long, they'll go blind. And luckily, it's reversible. You hear sort of horror stories of crazy old cat lady who had 72 cats, and it was too expensive, so she was buying bulk dog food, and all of her cats went blind. And she couldn't tell the difference because there's 72 of them, and she's 85 years old. But luckily, when you take the cats away, give them real cat food that has taurine in it again, they can start to see again. But so it just goes to show that this better term depends on what the context is. Is food with taurine better than food without taurine? If you're a cat, yeah. If you're a human, no big deal, no different really. And saturated versus unsaturated fats are the same way.
Does everything have taurine in it? Because I don't see cat food, like commercial cat food.
So the problem with taurine is that, so fresh meat has taurine in it. But if it's been killed and refrigerated for an extended period of time, the taurine actually degrades almost instantly. So cats either need to eat meat that's so fresh it's still moving, or be given cat food, or they'll eventually go blind. There still might be some amount of taurine left, or they could be going back and adding taurine after the fact. Once all the cells are dead, you can add taurine to raw meat, and then it'll work as a cat food. So if you're buying it specifically for a cat, if you're buying it from the butcher, from the grocery store, that's not ideal for cats.
Really, because my cat has major eye problems. I think I told you about this like months ago. She got me after 3 years, but it doesn't it?
It certainly could be contributing to that.
He's on his third cycle of antibiotics right
You switch to giving him some commercial cat food. You might be surprised. It might. I'm not saying it's a silver bullet, but it certainly, it can't hurt.
now.
Because
Something his vet should know, though. I feel like she's.
it should be, yeah.
All right.
I'm not going to throw your vet under the bus too much, but yes, the vet should know better.
Okay.
All right. So there are some questions about polarity that were actually relevant, so let's actually spend some time on these. How do we know if something is asymmetric versus symmetric? Does having lone pairs make a molecule asymmetric? Yes, absolutely. Having lone pairs will make a molecule asymmetric unless you happen to have the right number of lone pairs that turn something from being, say trigonal pyramidal into being linear. So if you think about iodine difluoride. Iodine difluoride, when you do the Lewis dot structure for it, we get a color that actually works. You wind up with a Lewis dot structure that looks like this. The electron geometry is trigonal bipyramidal, but by virtue of having 3 lone pairs, they take up all the spots around the equator here. And that turns it into being something that's purely linear. Now, all of a sudden, despite the fact that we have lone pairs and we have polar bonds, this is a non-polar molecule. So we still have to double check. Just being able to look at it and say, oh, it's got lone pairs, therefore it's asymmetric, is not always enough, because there are some cases where you can make something that's totally linear while still having lone pairs. So you have to double check. But for the most part, if you have just one lone pair, it's asymmetric. As long as you can look at whatever's surrounding your central atom, and as long as you have at least 2 different things attached to it, it's almost always going to be asymmetric. This is sort of the exception to that rule. If you happen to have the right number of lone pairs to make something be totally linear. Another common example would be Xenon Difluoride. Xenon Difluoride is going to be totally linear as well, because it's going to have 4 lone pairs around the xenon. So you'll have something that looks like because remember, all these lone pairs, they take up extra space around the atom, right? So they're going to try and be as far away from each other as possible. So if you have the right electron geometry and the right number of lone pairs, you can wind up with something still being symmetric with regard to where the electronegative elements are. But for the most part, if it's tetrahedral, we don't have to worry about this. There is no way that you can have a lone pair on something that's tetrahedral and not have asymmetry. It really only shows up in these 2 cases. When you have something octahedral with 4 lone pairs, or if you have something that's trigonal bipyramidal with 3 lone pairs. And the second we change this formula, so iodine tetrafluoride is going to look like, it's going to have 2 lone pairs, I think. Yeah, and then this one will be over there. We still want to double check it, or that's a fluorine now. So there's So in that case, now all of a sudden, is that symmetric or not? Is that going to have a net pull towards one direction of the electrons, or are all the fluorines totally balanced out? They're balanced, right? Or that would be what? That's xenon tetrafluoride would look like that. Sorry, not iodine. Iodine tetrafluoride would have only one lone pair, and then you do have asymmetry. It's xenon tetrafluoride. It looks like this. You wind up with all your fluorines being exactly 180 degrees from each other, and so it winds up still being symmetric. But in general, when you draw your Lewis dot structure, if you can point to it and say, hey, I have one thing that's different than everything else, that's going to be asymmetric. If you have an even number of things that are different, then you can wind up with them canceling each other out. So you might need to double check that in that case. But it really only happens once you get to trigonal bipyramidal or octahedral.
There was one before, and I think it had basically a pentagon around the center, and then two up and down.
Yeah,
If
that's
you
a
have two
really,
lone
we're not
pairs-
even going to deal with that one. That was sort of the challenge question for that Vesper lab.
Well, I just wondered if you have two lone pairs in that one, because then you only have 72 degrees around, so it's less than 90. So would those go like just up and down, and you have a
Right,
wall?
so let's see, what was,
Pentagon?
I'm trying to think of what, it would probably be a metal in the middle. Right, so if we had a bunch of fluorines around the metal and then a lone pair up and a lone pair down. So if you can picture this is sort of, I'll switch colors.
Is that the only case where you get the two lone pairs top and bottom? Then? It has a 72.
Exactly. So if you can see, it's poorly drawn, but there's a pentagon in the board and out of the board, and then something coming straight up and something coming straight down. In this case, this is another case where even though we have two lone pairs, the fact that they're the same, they're exactly 180 from each other, and these ones are all directly opposite of each other, this would also have symmetry. But this is going to be a really weird exception. We're not going to deal with anything that has 7 electron groups now that we're through that Vesper section for now. All right, but yes, that is the only case where you can also have where your two lone pairs will go. It's not the only case that's octahedral. Lone pairs are always going to try and be opposite of each other as much as possible. Okay, so they're going to go in whatever spots are the biggest, have the most room, with the fewest neighbors nearby. All right, so sometimes if you have an octahedral geometry with two lone pairs, that's the one that I drew a second ago. And that should be dashes. The two lone pairs are going to be opposite each other at 180 because that keeps them each with as much space as possible. So yeah, there are cases where you will get the lone pairs on the up and down, but it's going to be octahedral or that exception case, the 7 things.
This is all 90.
This is all 90, right? And if you put the two lone pairs directly next to each other, they're going to push each other away. It's going to rearrange itself into this shape. Moving forward, should we just use the electronegativity values on the chart given to us on our conversion sheet? Without having more details, I don't know exactly what the person was asking about, but I'm thinking it's referring to nomenclature. The answer is no. In general, it's the way we're going to approach nomenclature is just, do I recognize a positive charge and a negative charge? And if so, it's ionic. So for the most part, that means metal, non-metal. If you have metals and non-metals, it's going to be an ionic compound for the purposes of naming things. If you have ammonium is our one positively charged polyatomic ion. So if it's a metal or a ammonium, and then something with a negative charge, just name it as though it's ionic. Don't get out your electronegativity chart to decide whether it's ionic or covalent for the purpose of naming things. Right? It's useful for the purpose of telling what it's going to do if you try to dissolve it in water, say, but not for the purpose of naming things.
Well, that was my question, not mine. It was for the determining if something's polar, non-polar, or.
Oh, yes. For the purposes of determining whether something's polar or non-polar, the electronegativity values that are on your conversion sheet are good to go.
So like on a test, you'll only ask us about something.
Exactly. I'm not gonna, if I asked you something that was not on that list, I would give you the electronegativity.
She gets my question.
I see what you're saying.
Yeah, you're good, sorry.
I was looking forward to knowing we had nomenclature coming up, so I was thinking about nomenclature. Can you have a molecule that has both polar and non-polar bonds? Absolutely. But again, for the purposes of this class, one polar bond is all it takes to make the entire molecule polar. If you have at least one polar bond and you have asymmetry, for the purpose of this class, that's polar enough. Right? So there are cases where you can have a polar region of a molecule and a non-polar region. Fatty acids are one example of that. Or you have a bunch of polar bonds, or even something that has a charge, and then a whole bunch of carbons and hydrogens. This part of the molecule we would say is polar, and this part we'd say is non-polar. But for the purpose of just classifying it as polar or non-polar, the fact that it has one part of it is polar, that's enough. We just call it a polar molecule. All right, and if I don't get to your questions here, I do usually, as I've said before, I try to answer them in your questions, but I think that's most of the more relevant questions. And let's do one practice with problem solving here that takes into account some polarity questions and Vesper geometries and some math. So, noble gases, when they were first discovered, it was because a mixture of xenon and fluorine was in a quartz bulb. Quartz is just crystal glass. So, and it was placed on a windowsill and made a white solid eventually. They didn't know what this white solid was, but they were able to analyze it and say it was 77.55% xenon by mass and 22.45% fluorine by mass. So, what's the formula? I'll give you guys a few seconds before we start working through that. Give that a go. Think about how you could figure it out. The hint that I will give you is think about the formulas are not in mass, right? If I say H2O, I'm not talking about grams of hydrogen and grams of oxygen, am I? So maybe you need to convert from a mass into something that might be helpful for formulas. My hints did not help you, I could tell. So if I have an ionic, we've been doing a lot with ionic formulas, right? We don't balance these formulas. We balance them in terms of charge by adding grams or by adding what to each side? Electrons, or just how many ions from each side, right? If I say
you're adding a mole of it, right?
Moles. If I say these are the two charges, I need 2 chlorides for every 1 magnesium, right? Not 2 grams of chlorine for every gram of magnesium. I need 2 chlorine ions. So we want to get everything to moles. Because comparing masses doesn't really do any good. We need to know how many molecules or how many atoms we have of each type. I'll pause, give you a second, and then I'll...
So it's saying that 1 gram contains 77 point whatever percent and 22%, and we want to change that to moles.
Bingo.
Okay.
What was the first thing you said there?
Who's that? I don't know. That was
Said
wrong.
1 gram equals those 2%.
1 gram equals those. So basically, if you have a percentage by mass, pick an amount. say, okay, let's say I have 1 gram of this compound. How many moles? Use that to figure out how many grams of xenon you have, and then use molecular weight to figure out how many moles of xenon that is. Start by picking just a convenient number for your mass. 100. 100 is really nice, right? So you can say things like, okay, let's say I have 100 grams of this compound. Let's just call it exactly 100 for sig fig purposes. Well, for every 100 grams of that compound, I know 77.55 grams of that are xenon. And once I know how many grams of xenon I have, I can get to moles of xenon if I have a periodic table, right? What would we use on the periodic table? How do we convert from grams into moles? AMUs, atomic mass. Go to your periodic table, find the atomic mass of xenon, which is
Grams and moles.
grams per mole, right?
For xenon 131.3.
Right, so we started with, I picked an amount, and you could do 1 or 100. 100 is convenient if it's a percentage already. And we can say for every 100 grams of compound, 77.55 grams of it are xenon. And then we can say, okay, well now I'm in grams of xenon. And I want to cancel out grams of xenon and be left in moles of xenon. Xenon is one of those elements that if you say the name too many times in a row, it starts to lose all meaning in your mind. Xenon, xenon, xenon. I'm the only one who does that? No? Okay. What do we get for a number here? About 0.5 or so?
0.5906. And then fluorine is 1.2.
We can do the exact same thing. Take the same number we started with and just say, okay, for 100 grams, for every 100 grams of compound, 22.45% xenon. The fact that it's by mass means that as long as we have mass units on top and bottom, we can pick whatever units are convenient. It could be in kilograms, grams, pounds, whatever, as long as it's the same on top and bottom. So pick a unit that's convenient, since our atomic masses are in grams per mole. And so it's 18.998.
Got it.
Give me 2 more sig figs.
1.181, 1.182. So does that mean it's 2 to 1?
That's where we're going next. Remember what the original question was. What's the formula of the compound? We need to get the ratio of fluorines to xenons. So we put everything in moles. We can say, okay, well, I've got 0.5906 moles of xenon and 1.182 moles of fluorine.
Now you define out how many atoms.
Not necessarily.
You just divide it, right? And it's,
Yeah.
Yeah, whatever I have less of is probably going to have a subscript of 1 in our formula, because I have more fluorines than I have xenons, right? So if you take each of the numbers, whatever you have that's in there, and it can be more than just 2 components, whatever you have the fewest moles of, divide everything else by that number. And you should get either whole numbers or things that are really close to exact fractions. So in this case, 1.182 divided by 0.5906, it's really close to 2 to 1 ratio, right? Like maybe exactly 2 within sig figs.
out to the millionth, yeah.
Okay. So if we say, okay, 1.182 divided by 0.5906,
Oh,
we get a ratio that's going to be
Is 2.001.
and our units are moles of fluorine per mole of xenon.
So there's 2 F's for 1.
So before we understood how ionic compounds worked, and before we understood how covalent compounds worked, and Lewis dot structures and everything, this is how they figured out what stuff was, what the formula for things were. You literally took water, and if you applied enough voltage to it, you could get it to break down into hydrogen gas and oxygen gas, and you could measure the mass of both of them. If you knew the mass of oxygen and you knew the mass of hydrogen, you could work out what the ratio was by doing the same thing. Right, so this is still a really common way of determining. If you have an unknown, you just figure out what the mass percentage is of everything. There's different methods for figuring that out, and then you just figure out what the right ratio is. So we've used Xenon Difluoride as an example already today. So you might be able to come up with the Lewis structure from memory or count your electrons. If we're counting our electrons, each fluorine gives us 7, right? 2 times 7 electrons and 1 times 8 electrons for the xenon. So what was it, 22? So that gives us, that used up 16 of our 22, so we have 6 electrons left. So yeah, 3 lone pairs. So I did have the formulas wrong
We have to keep
earlier.
all the dots on the fluorines, right? For the dot
Yeah,
structure.
they still have the Lewis dot structure. You still want to draw these. You don't need to draw the loops, but you want to make sure that you don't lose track of them. They're not going to affect the geometry of the xenon. So the shape of the compound, the electron geometry, just count a number of things, right? We've done that lots of times, but for practice, this one gives us trigonal bipyramidal, or the one that looks like a trigonal planar with something going up and something going down. So you got something where everything's 120 from each other in the plane here, in and out, and then 90 degrees up and 90 degrees down. Dylan?
Because this is the shape of the molecules, isn't it just linear though?
Correct. So our electron geometry is going to spread these out. No, that's exactly where we're going next. We have 3 lone pairs. The lone pairs go on the triangle plane because that keeps them far away from everything else as possible, which means the 2 fluorines have to go up and down. So we will get a totally linear shape. Right? Despite the fact that we have 5 electron groups, it's going to arrange itself such that the 3 electron groups are away from each other, which makes the fluorines have to be 180 from each other as well.
So the molecular geometry is trigonal bipyramidal.
The electron geometry is trigonal bipyramidal, and the molecular geometry would just be linear.
So for C, we're just answering the molecular one, right?
Correct.
Okay.
You can't get to that without going through the electron geometry, though. Hybridization, we haven't talked about that in a little bit. That was the idea that we mix together different orbitals in order to give us the right number of electron groups. So when something was tetrahedral, we said it had 4 electron groups, and so we said it was 1 part s to 3 parts p. Right, because there's 3 pieces of a p orbital that can be mixed in and 1 s orbital mixed in. Is this sounding vaguely familiar? If you block this all out. So if we have 5 electron groups, we can't just make up 5 groups by using s's and p's, right? Because an s only has 1 part that it can add. A p orbital only has 3 parts it can add. So what's the next orbital that we would add?
5D.
D, and specifically it'd be the 5D for xenon, but it doesn't even really matter as far as predicting hybridization. D can go up to a total of 5 parts, but we only need to add in a total of 5 things. So 1 part S, because that's the lowest energy. 3 parts P, because that's the next lowest energy, and we need 1 more electron group. So we had 1 part V. So the hybridization here, for anything that is trigonal bipyramidal, is going to be sp3d. However many electron groups you have, you need to mix in that many orbitals. An S can only ever give you 1. A P can give you at most 3 orbitals. And so we need to add a D as well. If it was octahedral, it'd be sp3d2, because we would have 1 more electron group we needed to add in. Electron domains, electron groups, electron domains.
And that doesn't matter what energy level the elements are at.
No, this is the hybrid, yeah, because the hybridization is basically just another way of saying the electron geometry. Everything trigonal bipyramidal will always have the same hybridization. And everything tetrahedral will always have the same hybridization. Right, so it's basically another way of describing this. It's actually easier to remember, frankly, because we're so good at S than P than D now. You guys are good at your electron configurations. Rather than remember trigonal bipyramidal, you just call it sp3d. Right, it's a 1-to-1 translation. It's a direct translation. It's 2 sides of the same coin. Trigonal bipyramidal is describing it in geometry terms. sp3d is describing it in orbital terms. It's the same shape. Is the molecule polar? Last thing, and then we'll take a break. No. We already used this as an example of something that has 2 different things attached, but has symmetry, right? The fluorine is more electronegative than the xenon by enough to make this a polar bond. It has polar bonds, but the 2 polar bonds are exactly opposed to each other. So the fact that they're in exact opposite directions tells us it's symmetrical. So it has polar bonds, yes, but it is symmetrical. Therefore, it's nonpolar. Right, so hopefully that was the main idea with the quiz over the weekend, was the idea that you have to say yes to both of these things in order to make it a polar molecule. Right? Polar bonds, but symmetric, it's nonpolar. All right, questions? We'll do more practices with this. We're going to get back into doing more word problems, because now that we have a conceptual basis, we can actually calculate things that we can measure in lab. So let's take a break. Let's come back at 10 after. And then we'll start talking about formulas and reactions more. Just wait.
Sean, are you adding these slides online?
I skipped past the solution stuff. We'll do that next week. We'll get into this. This should be in the slides for today. It just passed all of the.
Once I looked online, the slides are available to print out. So this is what,
Oh, okay.
this is all the.
Sorry, they were. It starts right after that one.
Yeah, because I looked up, because I normally try to print them out right before, but,
They should have been up there. Maybe I posted the wrong ones.
because on Thursday, it just said Thursday slides, but it didn't have anything to download.
Today's Tuesday of week 8.
Oh, that might have been it.
Because this was
That's
those are Thursday slides
Oh, well
of
played.
week 7. Yeah.
I'll be right back.
All right. But yes, they should be posted. I'm skipping over some of the slides because we'll talk about solutions and concentration after we talk about reactions so that we're ready for next week's lab because we'll actually start doing more reactions in lab now that we understand how molecules work and how compounds work to some extent. So this is one of the core pieces of the Dalton's atomic theory. One of the 4 postulates was atoms are not created or destroyed, but their arrangements can be changed. So basically a chemical reaction is just anything where we're rearranging what bonds we have, or rearranging that we have a set number of pieces, but if we change how they're all connected, we can make different compounds. So for instance, this is an organic compound called butane, like in a lighter. You take butane and you let it react with oxygen, you make carbon dioxide and water. We still have all of the same pieces. We still have carbons, hydrogens, and oxygens before and after. We're changing how they're arranged though. And that's all a chemical reaction is it's a before and after picture where we're changing what's connected to what.
The H2O coming off butane, is that like when you refill your torch and the thing gets all like frozen?
No, that has to do with if a gas expands too quickly, then the temperature drops.
Oh.
So that's an unrelated phenomenon that we will get to in this class, but just not yet. This is actually, we don't usually think of, this is called a type of reaction called combustion reaction. This is burning things. We don't think of combustion reactions as putting out a lot of water because they usually put out a lot of heat as well. So the water that comes off of these reactions is in gas form. But if you've ever started your car on a really cold day and then you went outside a few minutes later and you noticed there was a big wet patch on the driveway right underneath your tailpipe, that's the condensation from the gaseous water coming out of the tailpipe hitting the cold driveway and turning back into being a liquid. So it's also why sometimes when you see airplanes flying through the sky, sometimes they have a contrail balloons. Anybody know what contrail stands for?
Condensation.
Condensation. So basically, if you have an airplane flying through the sky and it's cold, when the air leaves the engine from the airplane, it condenses, yeah, and you wind up forming clouds. And if the conditions are right, you can actually wind up creating an entire large cloud system. Basically, and what's happening then is not that they're adding some chemicals to the mix that are, going to mind control you or, cause global warming or anything like that. It's basically chemtrails. It's basically just that that area of the sky was already about to form a cloud. The conditions had changed such that there was a moisture in the air, the temperature changed, and all that it took was a plane flying through it and adding a little bit of a place to start forming a cloud. And something that probably was going to happen anyway, but it's just really easy to see it when it's the plane that's doing the disturbance and causing those clouds to start forming. But it's not necessarily anything nefarious. It's totally explainable with normal phenomena.
They do add zinc to JP8 fuels and jet fuel nowadays just to produce condensation. But that's just to create weather kind of thing.
They do a little bit of, and actually Nevada is actually one of the leaders in cloud seeding, which is basically, it's a lot like making snow at the ski resorts.
Yeah.
You add a little bit, small particles of things that don't react with much of anything, basically just give the moisture that's already in the air a place to condense. Because you can't really start making a water droplet without a place to have it start forming. Right? So by giving it just a tiny little place to start a water droplet, by adding these tiny nanoparticles into the air, you can actually cause clouds to start forming on purpose. And so actually Nevada's been using that to try and increase the amount of moisture content, or the air, what's the word I'm looking for? Precipitation, that's the word. Over areas that are high farming areas. So, all the melon farms in Fallon and Fernley and things like that. They've been doing cloud seeding above those to try and get to alleviate some of the drought conditions. By getting, basically, we're not making water out of nothing, we're getting the water to fall where we want it to fall by adding these cloud seeding conditions. And they do, I didn't know that they were doing that on purpose.
Yeah.
With the fuel, but it is pretty common in jet engines in general, just even without adding anything. A lot of times the disturbance is enough to cause these water molecules to start turning into these condensation droplets.
Well, it's like you said, it's not really affecting anything. It's just small particles that water can condense on.
Right,
Yeah.
right. The reason you see it sometimes and not other times is sometimes the weather conditions just aren't favorable. It's too dry or too cold too dry or too warm up in the upper atmosphere for clouds to form. And so an airplane can fly through sometimes without causing a contrail. But it's not, because sometimes they're trying to control your mind and sometimes they're not.
Rain is a good conspiracy.
Yeah, birds aren't real.
They aren't.
Wake up,
What is
sheeple.
that?
I'm not even sure if it's a real conspiracy theory, if it's a joke conspiracy
It's a meme.
theory. It's a meme, but I'm not sure if it started as a real thing.
It could have.
Yeah.
It's basically the idea that the government has replaced all birds with robots that look like pigeons so that they can monitor your every move. Yeah. Anyway.
Yeah, no, that started. Yeah, that started. It was a pretty funny meme too. Like there was birds don't exist.
It's like anything on the internet, right? That's really hard to draw the line between sarcasm and somebody making a legit statement.
Yeah, like originally Flat Earth was just like a joke, and then people started actually believing it.
Right. Exactly. You have to be careful on the internet. You ever think somebody would go do that? Just go on the internet and tell lies?
Yes.
Anybody else grow up watching Arthur on Channel 6 or what, PBS, whatever it was? It's one of my favorite internet memes of all time. Somebody do that? Just go on the internet and tell lies? So when we have these chemical reactions, back to things that are relevant to this course, we have a couple new vocab terms we use to describe them. The before picture is referred to as the reactants. It's the molecules that are doing the reacting. And then you have an arrow, and chemists get very particular about their arrows, and we'll talk about why as we get further in here. And then what we make is what's called the products. right? So that's easy enough. You produce the products from the things that are reacting, which we call reactants. Reactants make products. And the arrow in the middle, we call it a reaction arrow, and it's very specific, and we're basically indicating something happened. So it can be a really long period of time, it can be a very short period of time, but it's just giving us a before and after look. And then, exactly. The other thing that we indicate here is we indicate the phase of these molecules generally. If it's a complete chemical reaction, we don't just want to say what it started as and what it ended as, we also want to say what phase it was in, meaning solid, liquid, gas. Right? Because some things won't react as a liquid, but they will react as a gas. Or they'll change how quickly it reacts, because if something is a solid reacting with a gas, it doesn't have as much surface area that it can react with the gas. Versus if you have something that's two gases reacting, it can happen very quickly. Right? And so we have actually 4 phases that we're going to list here that are really commonly abbreviated. Solid, liquid, gas, all pretty self-explanatory. Explanatory or explanatory?
What's the difference between aqueous and liquid?
Aqueous means it's dissolved in water.
Ah,
So water is the most common liquid that we use to make solutions. And again, I skipped the part about solutions. We'll talk about solutions in more detail. But since water is the most common thing we use to make a solution, it gets its own phase. Aqueous just means dissolved in water. So when you take salt as a solid, then you throw it in a pot of water, it dissolves. We can write that as a chemical reaction. Solid sodium chloride reacts. It's barely a reaction, but we can still write it as a reaction. It's more of a physical process than an actual reaction, since we still have the same compound before and after. But all that changed, we went from being a solid to being dissolved in water.
On our big packet thing, I noticed that everything that was labeled aqueous was an acid. Is that
Correct. So exactly. So that's, and remember at the beginning of this lecture, after we talked about acids, I said if it's a gas, we name it as an ionic compound. And if it's aqueous, we name it as an acid. Basically, you cannot get liquid acids to be 100% pure. So you're never actually going to see an acid labeled as being liquid. You will always see it labeled as being aqueous.
and a hydrate isn't?
You know, a hydrate is a water molecule that's dissolved in a solid. It's not really dissolved, it's basically taking up the extra space in that crystal structure. So a hydrate, we would still call it a solid. If atoms cannot be created or destroyed, but they can be rearranged, what's wrong with this equation?
it's not balanced.
Yeah, we've got 4 carbons on the left and only 1 on the right. Right, so I think you guys were all waiting for that. Everybody had their answer ready, which is good. I like when you can see where I'm going. So if the atoms are not created or destroyed, the reaction has to be balanced. Meaning whatever you start with and whatever you end with have to have the same amount of atoms.
There's a bunch of different ways you can do it, including matrices.
You can use linear algebra to do this, but that's really a Larry Green thing. He likes to claim that it's easier than just doing guess and check, but I like guess and check. It's not
really
easier.
isn't.
I will qualitatively say that as somebody who took linear algebra, it's not easier to use linear algebra to balance equations. I will teach you the better ways to do that. So if we're looking at this initially, if we just assume we have one of all of these, we have 4 carbons, 10 hydrogens, 2 oxygens on the left, but on the right-hand side, we have 1 carbon, 2 hydrogens, 3 oxygens. So what we're going to do, we can't just stick a 4 right here, because now it's not the same compound. We had a reaction that was butane plus oxygen goes to carbon dioxide and water. This isn't carbon dioxide anymore, right? I changed what it is.
Texture, it's
You can name it if you want. Tetracarbon
Check your carbon
dioxide. It's not something that really exists though. So as a result, we don't want to just balance things by sticking subscripts. Once you have your compounds, we only are going to be dealing in whole numbers of each molecule. So you need to add however many molecules you have in order to make all the carbons balance out. So for instance, instead of sticking a 4 right here, I can't do that because now it's not carbon dioxide, but I can put a 4 right there. And say I have 4 molecules of carbon dioxide. Right, so I'm basically just, if we go back to, well, let's save that analogy for a second. I started with 4 carbons, and I'm making carbon dioxide. So let's say I have 1 car, and I want to make unicycles out of it. How many wheels on each unicycle?
1.
Just the 1, right? So how many unicycles can you make from 1 car?
4.
Assuming we could use the same wheel, that'd be an interesting unicycle. But yeah, we could in theory make 4 unicycles from 1 car. But we just changed how many oxygens we have now. So we need all of these to be balanced. So just by doing that, by having 1 butane makes 4 CO2s, I balance the carbons. But we don't have, but now our hydrogens and our oxygens aren't balanced yet. So this is what I was saying, it's glorified guess and check sometimes. We're going to pick a place to start, pick an atom to start with and balance it. And then pick the next atom and balance it. And you basically are just going to go back and forth before and after until you get it so that everything matched up. And it goes faster than you might think.
Wouldn't the easiest place to start be the highest number? Just to balance that out first?
So the highest number, you mean whatever the
So,
biggest
like,
molecule is?
Yeah, so like hydrogen, for example, has 10 atoms in that molecule, so that would be the easiest one to balance. Just 5.
Not necessarily. I usually just start with whatever. So I think about what I want to do last. One of these molecules, I can change the number in front of it without changing anything else, which oxygen, right? If I can change the number in front of oxygen without changing anything else, then forget about oxygen until we get the carbons and the hydrogens done. Right? And then we can make oxygen be whatever we want to without throwing everything off and undoing all of our work. So it's basically you start from whatever the biggest molecule is, whatever molecule has the most pieces to it, and start balancing those pieces. And you save whatever the smallest molecules are for the very end, because usually those are the ones you're going to be able to change without ruining anything else.
So the
Well,
smallest.
this about to be, sorry, keep going over the question.
No, go for it. You first.
No, it's just like we're gonna ask.
I was gonna say.
Okay, so yeah, where are we going with this?
I was gonna say that water, based on what you were just saying, is bigger than carbon dioxide, so that'd be easier to balance than carbon dioxide.
6 of one, half dozen the other, right? We can add a coefficient here without changing carbons. We can add a coefficient there without changing hydrogens, so it doesn't really matter.
Yeah, it doesn't matter which.
As long as you save oxygen gas for the last part.
But that adds another step going from.
You just have to pick a place and start. And a lot of times you'll be surprised how often things will work themselves out if you just pick an atom and start. So we started with carbon just because it was furthest to the left. And we want to save this to the end. So now ignoring carbons, our carbons are balanced. So let's ignore carbons. Let's balance hydrogens. We have 10 hydrogens here. What do we need to do?
5 right here.
Each water has 2 hydrogens, so we can make a total of 5 of them. So now carbons are balanced, hydrogens are balanced. All that's left to do is oxygens, right? And we can change oxygens without messing with anything we've already fixed.
Ideally.
Not in this one. Why?
Because there's 5 oxygen with H2O, so you gotta double it to make it 10 H2O. Yeah.
Because we can only deal in even numbers of oxygens. Because we can't have half of an O2 molecule. So if we have an odd number of oxygens over here, it's not going to balance. So what's the fastest way to make an odd number even? Double it. Because this is a lot like an algebra equation. If our carbons are balanced on both sides, carbon before equals carbon after. Hydrogen before equals hydrogen after. We can treat it like an algebra equation where anything we do to the left side, we do it to the right side, and it'll stay balanced. Right? So if we had 1, 4, and 5, 2, 8, and 10, and it's still balanced. And now we have an even number of oxygens on the right-hand side, because it was an odd number and we doubled it. So it has to be an even number now. So we have a total of 26 oxygens over on this side now, 16 from the CO2. We have 8 CO2 molecules, each of which has 2 oxygens. So 8 times 2 is 16. And we have 10 oxygens in the form of water. It's really hard to distinguish my zeros from oxygens. We'll do that. How about that?
There you go.
So that gives us a total of 26 oxygen atoms in the form of O2, so we need 13 of them. Right, so when it's just start totally blank, it seems like a little overwhelming. Where do I even start balancing this? Just pick a place. Start doing it. Save the simplest molecule for last. And a lot of times, if I gave you a real reaction, which I will always try to do, then usually it will wind up working itself out in a lot of ways. Where if you've waited, if you will do somewhere, I wind up making 6 of these because I had 6 over there. Just when I balance everything else, it automatically will balance the last element sometimes. Right? So a lot of times it's not something you need to worry about. You just got to start. You start making it the same on both sides, and it works out better than you think. All right, the biggest pitfall to watch out for. This is all kind of, it's abstract when we're talking about atoms, but it's really just conservation of mass. Whatever you start with, you have to end with. If you started with something, it has to show up on the product side too. Just total up your numbers before and after. Right? If it's balanced, same number of atoms on both sides of each type. All right, and these numbers we put in front, it's just like the number that we put in front of the hydrates. It's called a coefficient. It's basically telling the whole number of a specific compound. The subscripts are telling you how many oxygens are in each molecule. The coefficient tells you how many of those molecules you have.
Does temperature and dryness of the air affect how many oxygen atoms there are?
It will not affect how much oxygen there is. Your altitude will affect it to some extent, which is why you have to have a different fuel mix for something like an SR-71. Has to have a different fuel mix and has to have, in order to be able to burn fuel well at all altitudes, it has to be able to regulate things. But that's part of what a fuel injector does. A fuel injector in an engine basically regulates how much fuel compared to how much oxygen there is. If you have an engine that has a carburetor that doesn't have a fuel injector, you actually have to tune it differently based on whether you're at altitude or at sea level. You have to change the fuel-air mixture because we have less air up here. But it won't change the ratio of how many oxygens we need to burn things properly. Because this is based on making sure everything adds up to the same before and after.
When you're writing this, could you put the number, just actually for the next page, that next example, the CU 103 with the parenthesis 2. If I wanted to give everything double it, can I just put parentheses around the whole thing with a little 2 in the bottom corner, or do you want the 2?
We want the coefficient to indicate that we're not changing what the compound is. So what I heard you ask is, instead of doing a coefficient, can I write that?
Yeah, because it's not the same thing.
We don't want to do that.
Okay.
Subscripts we specifically use for saying what the makeup of a compound is. And the coefficients are how we indicate how many of that compound we have. I mean, mathematically, it's not wrong, but it's not the way it would ever be written in the real world. It gets too confusing.
Gotcha.
And so for any of these, if I'm remembering properly, there might be one of these that's kind of tricky. The third one.
Another way to keep changing. First, we look at simply.
So if you start with two, if you got two sodiums for this first one, you got two sodiums on the left, we can't change that coefficient to balance things because then we're changing what the compound is. If it's sodium sulfide, it's got to be Na2S. So if we're making something that just has a single sodium, we know we have to be making two of them. Now, our sodiums are balanced. We've got one sulfur on the left, one sulfur on the right. We've got one copper on the left, one copper on the right. We can, here's another trick, is that polyatomic ions, if they're not being broken up, if it's the same polyatomic ion before and after, you can just balance nitrates as one big group. You don't need to pull out nitrogen and oxygen. Because if all of our nitrogens on the reactant side are in the form of nitrate, and all of our nitrogens on the product side are in the form of nitrate, then everything's staying as nitrates. We'll just balance it in terms of nitrates. So two nitrates on the left, two nitrates on the right. So this one's good. And just like everything else, if we don't write a number in front of it, we can assume it's 1. We have 1 sodium sulfide plus 1 copper 2 nitrate. Turns into 2 sodium nitrates and 1 copper sulfide. Right. Or it's not wrong to write the 1s. It's just a little redundant. I guess the exception is when I'm writing tests to remind you that you need to balance things. I will frequently write them like this. If I give you a blank, I kind of want you to write a 1 in it so that you're not indicating that there's a 0 there or something. But if it's not written as having this big blank in front of the molecule, you can assume that if there's no number, it's a 1. Otherwise, it's like trying to write a fraction. You could just write 2 and it's assumed to be over 1, but if I write 2 over and I ask you what to fill in there, you kind of have to put the 1 to make it right. It's a little bit nitpicky, I apologize, but that's usually what I'm looking for. When in doubt, put the 1. Number 2. This one's interesting because we have hydrogens and nitrogens are all we have to work with, but we're making 2 different compounds that both have nitrogen in it, which could get weird. One of the things you can do is, remember when we balanced the first one, I said, oh, well, we're making an odd number of oxygens and we can't do that. That was our hint that we were going to need to double something. We've got 4 hydrogens on the left, right? Which means whatever we do, we have to end up with an even number of hydrogens over here. Not just an even number, it has to be a multiple of 4. Right, so if we just double this, then we get H6. There's no way we can use a whole number to get to 6 hydrogens either. So we're going to need to make it 3 and 4. Now we have 12 hydrogens on each side. Right, so it's a little bit like finding lowest common multiple. And if we do that right, that gives us a total of 6 nitrogens on the left, 4 nitrogens there, and then we had 2 more, right? So that's what I mean about sometimes if you balance out some of the atoms, the rest of them take care of themselves. Right? And we saved the simplest one for last because now we could change the number here without messing up with the hydrogens. The hydrogens are good now. If we needed to add another coefficient here, it wouldn't mess up the hydrogens. HCl plus O2 goes to water and chlorine gas. Well, again, look at our subscripts. We have to make an even even number of chlorines, right? So at the very least, we know we have to do that. And then that balances our chlorines. Hydrogens are balanced. Oxygens aren't though, right? So just like with the combustion reaction, we've got an even number of oxygens here and an odd number there. So we're going to have to double everything. All right, so make that a 4. Then this becomes a 2. Then this becomes a 2. Hydrogens are good, chlorines are good, oxygens are good. Again, it's going to take practice, and some people can sort of intuitively see how things are going to work, how the ratios and the fractions are going to work. Some people, most people, it takes practice. And it feels like glorified guess and check. Yes, there's a procedure to it, but it's going to be a little bit different every time. It's just a matter of, okay, start making things the same on both sides. And the second you can make it so that you've got the same number of every type of atom on both sides, boom, you're done. So you always have a way you can check your answer. I'm not saying that on a test that you will always get 100% on balancing the reactions, but you should at least know when you're wrong, which is an advantage in and of itself, right? It should not come as a surprise that you messed up balancing, because it's really easy to check. I have an extra chlorine there compared to here. All right, how about this last one?
1, 2, 1, 1.
Boy.
Well, how do we get there?
We have 2 H's, 2 Cl's, 1 Fe, 1 S. Fe and S are by themselves, H and Cl by themselves, so you just need 2 H2 and 2 Cl.
I'm not saying you're wrong, just telling you to slow down so I can follow what you're saying. That was fast for me.
Speed up, Sean.
I should have taken more caffeine today. Yeah, so we got to pick a place to start, right? So where did you start, Jordan?
Oh, I just looked on the right. Oh, I just looked.
You just looked, you saw 2 chlorines over here?
2 chlorines, 2 H2s, and I see that the Fe and the S are by themselves. And
Okay,
those
so
are
stop
what are
there.
those.
Let's pause. You saw that there are 2 chlorines and 2 hydrogens. And over here, the only chlorines and hydrogens are in the form of HCl. So that right off the bat tells us this has to be a 2. And then if we're lucky, that's all we have to do. But we still want to double check. 1 iron, 1 iron. 1 sulfur, 1 sulfur. Hydrogens are good or chlorines are good. So we're done.
So when you give this to us on the test, it doesn't matter if it's a gas, a solid, a liquid. If you give it to us like this, that doesn't take.
It does
anything
not affect the balancing one bit.
Okay, cool.
Balancing will be the same regardless. It can change how the reaction actually happens in the real world a little bit.
Okay.
For instance, if you're dealing with gasoline when it's 20 degrees outside, you can pretty easily put out a match in a bucket of gasoline, right? If you tried to do the same thing when it's 90 degrees outside, you're going to light your whole self on fire. So changing the conditions can change things, but the balancing is the same either way.
Yeah. Polar temperature makes it harder for chemical reactions to occur.
Right. When we get in third quarter, we'll talk about rates. And rates are all based in the calculus, but we're not going to present it as calculus, so don't worry if you haven't had calculus. But basically, we can talk about how fast things will happen just in terms of things like temperature and energy. All right. So I want to go through these. This will be fast for 10 minutes, but it's one of those things where if you've seen it more than once, that's a good thing. So we'll go through it fast and it'll seem confusing, and then we'll go through it in more detail again next week. Basically, our reactions, depending on what textbook you read, reactions get chunked up into a lot of different possible ways to categorize them. There's as many different ways of categorizing reactions as there are chemists, because everybody has their own specific way that's relevant to their field of study or the way that they understand things. So I'm going to give you the way that makes sense to me. I'm not going to use terms like a double replacement reaction or a single replacement reaction, because those are not a great way of understanding what's actually happening. The way that I break these up is they're in one of 2 categories. It's either a, what I call a complexation reaction, meaning we're just changing the way things are fitting together, but we're not really changing what anything is. If it started as a nitrate, it's still going to be a nitrate. It might be a solid instead of being aqueous now, but really nothing is really changing identity. Everything is, you can still pretty clearly identify products versus reactants. Everything is still the same before and after. Right, so these are a lot like putting together Lego sets. You have a set number of pieces, you can change how they're arranged to make the castle version or the pirate ship version, but you're still limited by these are the Legos I have to work with. Oxidation reduction reactions are like taking your Legos and melting them down and making new Legos. Right, so these are the ones where things are dramatically changing before and after. Right, and our official definition of an oxidation reduction reaction means that electrons are changing hands. Basically, since nuclei don't really change in this class, at least outside of the nuclear chemistry section chapter, the only thing that's really can move are the electrons. So if the electrons move, it's an oxidation reduction reaction. If the electrons all stay put, we're just rearranging how everything's stuck together. That's a complexation reaction. We're changing what's complexed with something else. And I don't mean like it's complex like it's complicated. I mean like you're making a complex because these two things stick together. All right, so, and I'll give you examples of each of these. For the complexation reactions, no change in atomic charges. A molecule might change, but that's because we did something like add an H plus to it, like with our polyatomic ions. All right, so because nothing is changing, none of the atoms are changing charges, it's not really a reaction. We're just kind of rearranging how the pieces fit together. All right, so the simplest one is called an acid-base reaction. So what did we define an acid as earlier?
Something attached to hydrogen.
Something that has hydrogen attached to it, right? Basically enough hydrogens to make something neutral. Really, an acid-base reaction just means that you're moving an H plus from one thing to something else. Everything's still the same other than where that H plus is attached. Right, so for example, if we had sulfuric acid and say a hydroxide, might as well practice our polyatomic ions while we're working on this. If the sulfuric acid gives away an H plus to the hydroxide, what are we going to make?
H2O.
Right, we took an H plus and we stuck it on hydroxide. That makes the charges balance out, right? So we're going to make H2O, and we just took one H plus away over here, right? So now it's hydrogen sulfate. Nothing really changed identities. It's a sulfate there, it's a sulfate there. It's just missing one H plus.
So for ions, we would put the phase.
But yeah, we would. So this would be aqueous. We would want to put the phase on all of these. When I get lazy or when I'm trying to go fast to explain something else, sometimes I forget. Always ask for clarification though. We would not put, if it's water dissolved in water, water can never be aqueous, right? Because when water is dissolved in itself, it's not a solution, it's just water. So water is just liquid.
So that's just by our standard 200.
By our standards here on Earth. If you had water dissolved in ammonia, for instance, then you could say, you know, if we lived on a different planet where ammonia was the most common liquid and water was rare, we might have solutions where we had water dissolved in an ammonia. I won't try to guess what they would name something, an ammonia-based solvent, but it would be water dissolved in ammonia, and then we would have a different subscript for it. Sorry. But that's neither here nor there.
Or like the weird ices that form at like high temperatures, like ice 2.
We're getting there. You got to get through solids first. I think that's the beginning of 102. We'll start talking about phases and how you can have different types of solids as phases. So when we have an acid-base reaction, it's pretty easy to recognize once you know what the clues are. We're looking for moving one hydrogen ion. And so you should still be able to clearly recognize the same pieces before and after. And the charges might be off by 1. Right, so sulfuric acid is just sulfate with 2 H pluses. This is sulfate with 1 H plus. Hydroxide is an oxide with 1 H plus. This is an oxide with 2 H pluses. Right, so as soon as we can recognize the charges on the atoms are not different, all we did was move an H plus, it's going to be an acid-base reaction. The other kind are even easier to recognize once you know the clues. It's what's called a precipitation reaction. And a precipitation reaction just means that when you mix two things together, you make a solid. You mix two solutions together, and the result is something that doesn't dissolve anymore. And so precipitation reactions are always going to look like you mix two aqueous solutions and you make one solid as a product. So for instance, if you mix salt water and silver nitrate, what we really have when we have these ionic solutions is we have sodium ions floating around surrounded by water and chloride ions floating around surrounded by water. If you happen to make a combination that doesn't dissolve in water, then you make a solid. So for instance, silver chloride doesn't dissolve in water. So if you take these two solutions and mix them together, you're going to make silver chloride as a solid because it won't stay dissolved in water. And whatever else is there is still there. The sodium and the nitrate are still there. They're just both still dissolved in water. So if it's a precipitation reaction, again, no charges changed. We had nitrate before, we still have nitrate. We have chloride with a -1, it's still chloride with a -1. We just went from it being dissolved in water to it being a solid. Right, so again, no electrons change hands, which is what puts it in this category of being a complexation reaction. We're just changing the arrangement, not changing the identity of anything. And just to give you the comparison, and we won't go through all these since I know I have 30 seconds left. Anytime you can look at something and you can say that atom changed charges, it's a redox reaction. Redox is the shorthand for oxidation reduction. I don't know why they switched the order. Other than redox is easier to say than oxred. A redox reaction, so if you start with sodium with no charge, sodium metal, and it goes to being a sodium ion. We moved an electron to do that. That means it has to be a redox reaction. Zinc started as a +2, and now it's 0. The charge on the zinc changed. On the individual atom changed. Therefore, it's a redox reaction. That's our very clear defining line between these two classes of reactions. Do electrons change hands or not? All right, we'll end there. Thursday's lab, or today's lab, look online. You have until next Thursday to do the nomenclature assignment, and I think you have all the tools you need, including the key. But let me know if you have any questions, and we'll go over some of the trickier ones. And Monday, Wednesday lab, I'll see you tomorrow.
Polyatomic test, is that Tuesday or Thursday?
Polyatomic ion quiz next Tuesday. Week from today. The nomenclature assignment should help you study for that.
ICA from last week's data.
The periodic table assignment?
Yeah.
Last Tuesday?
Hang on 1 second, let me stop recording. What's up?